Hello and welcome to my YouTube channel. Today I'll be looking at another theorem. I've talked about other theorems in the previous video, so you can go and watch them. Today is going to be on maximum power transfer theorem. And we are going to be using a simple circuit diagram in order to explain this theorem. You can see here, and this is a simple circuit diagram. I have the voltage source, and this is the source resistance, and I connect the load resistance RL. So you can think about this as just a battery, right? The battery is having internal resistance, which we consider to be the source resistance. Then you connect your load, right? So a battery connected to, let's say, a light bulb, right? Now with this simple circuit, our aim is to find the maximum power transfer dissipated by the load resistor here. And to get to this point, right, what we tend to do is that we can start by calculating the power dissipated by the load resistor from this simple circuit. And that power is going to be equals to the current passing through the load resistor squared times its resistance, which is and that will give us this formula. Now, when it comes to the current, we can replace the current, right? Because we can calculate the current here from the simple circuit, where we get current will equal to the voltage source that we have here over the equivalent resistance of one RS and then RL. And RS and RL are connected in series, so the equivalent resistance will just be the sum. So I'll have VS over RS plus L, then we square it because we have the current squared here, times the load resistance. Now, this is how we calculate the power. Since we are interested in the maximum power, that means here we think about the load resistor here being a variable resistor that operates within a range. For example, let's say operate from 0 to 100 ohms, meaning within this operation range, you can select or adjust to any resistors within this range. So in order to get the maximum power, meaning I can start from 0, put the value for the as my load resistance, right? Load resistance that I have here. Then after that, I'll pick another value within the range of operation of the variable load resistor and then calculate the power again, right? So I can start from 0, 1 up to the 100th value within the range of operation of the variable load resistance that I have. So once I'm done, then I'll look through all the various powers that I've calculated and then pick the maximum power amount, I mean the highest amount of power dissipated. But in order to avoid all this huge amount of work in carrying out this activity, what we tend to do that we can make use of our knowledge of mathematics, right? If you look at the power dissipated by the load resistor, you can see this is resemble a quadratic equation. So we can just have a sketch of a quadratic equation in a curve of quadratic equation. So we have a graph here. So we have something of this nature. Now, when it comes to this graph here, that resembles our power dissipated. That's the power dissipated by the load resistor. You can clearly see that we can get the maximum power, or we get the maximum power when we are at the top of the curve, right? This is the curve, right? And that is going to give us the maximum power. And then we can now get the corresponding value within our range of operation of our load resistor to get the maximum power. So in other words, we can do calculation for this, right? How do we do the calculation? Since this is a quadratic equation, at the very top of the curve, that means the slope becomes 0 because at the top of the curve, you have a constant value. So the slope becomes 0. That means I can differentiate the amount with respect to the load resistance and equate it to 0. Then I'll try and get the value of the load resistance that is going to give the differentiation here to the 0, right? That will give me the maximum the value, right, for that very resistance, right, of my load resistance. Now you can do this. So you differentiate for this. You can see here to do the differentiating. Yes, what differentiate the top, right? VS R, and then after they multiply by the denominator, which is this, and then minus, we differentiate the denominator, and then multiply by what VS squared times the load resistance, which is here, and then over RS plus RL squared, right? Meaning, so you have RS plus RL squared, then you square it again, you get raise the power of 4. Then if you go through all the mathematics and finally you get the load resistance being equals to what the source resistance. So what that means is that if we want to know the maximum power dissipated by the load resistance in this simple circuit, what that means is that we have to select our load resistance to be the same as the source resistance, right? So let's say the RS here is 75 ohms. That means if I want to find the maximum power, I'll just pick what? The source resistance, the load resistance will also be what? The same, which will be what? 75 ohms. If this were to be 100 ohms, meaning I have to select the load resistance was to be 100 ohms. And this will allow us to get the maximum power. And that maximum power, we can even simplify this very formula, and then we will get that maximum power. And it's going to be equals to this maximum power. Since RS equals to R, L is equals to RS, I can just write VS squared over 4 RS, right? Because this one will cancel together. So with this formula, that will allow you to get the maximum power straightforward, right? Anytime you just know the source resistance. Now that you've gotten the basic understanding when it comes to power transfer theorem, we are trying to take a look at another simple circuit diagram. This time quite different from the first one. You can see here, now I have another circuit. I have voltage. I have R1, R2. Then I have my load resistor here. So this one doesn't resemble a simple circuit. So which means that we have to try and then what? Simplify the circuit so that it resembles the first one that we're using, right? And one way we do it by using what Thevenin's theorem, right? Because we know that when it comes to Thevenin's theorem, we have a voltage in series with the resistor. That voltage refers to as Thevenin's voltage. And then the resistance is called Thevenin's equivalent resistance. Then that will resemble our equivalent circuit for the linear active circuits, right, of our circuit diagram. Then we connect our load and then we can now get the power, right? We can get the maximum power. And that maximum power, as you can see here, the formula was what? The voltage was Vs squared over 4 times Rs. So when it comes to this circuit diagram, this simplified circuit diagram, you can see here our Vs is going to what? Vth. When it comes to Rs, that is the source resistance that correspond to what? Rth. And then the formula now becomes Vth squared over 4 Rth. That will give us the maximum power dissipated by the load resistor, right? Now that we know this, we can try and then what? Just try and calculate Vth and Rth from this circuit diagram. And when it comes to Vth, is the open circuit voltage. What that means is that if we were to remove the load resistor from this circuit diagram, you can see I now have this open terminal, right? Plus and minus here. And the voltage across terminal VA, right? The VA, we call it the open circuit voltage. And that is what is also our VTH. So what that means, once I remove the load resistor, I'll look here And if you are standing in R2, you see that will just go up. The voltage across VT will be the voltage across R2. And we can use voltage divider to get the voltage across R2. Because if I have a voltage source, voltage here, then here is open, no current pass through, meaning the same current will pass through R1 and R2. So R1 and R2 are connected in series. Then I can use voltage divider rule. So I'm entering the voltage across what R2 down what R2 over R1 plus R2 times the voltage. Yeah. Then we try and now get the what RTH from this very circuit diagram. And we can obtain it by making sure that all independent sources in this linear active circuit, they are all turned off, right? Meaning we make all of them to be zero, right? So you can say I have a voltage source. When you come to a voltage source, you make the voltage zero by short circuiting the voltage. What this simply is that I'll take a wire, right? And connect it, right? Connecting wire to this. So we indicate it this way. This means I'll short circuit the voltage and that voltage here is zero. Now just look at the circuit diagram. Then try and get the equivalent resistance from the circuit diagram. And you can see that R1 and R2 will be connected in and now equals to what? The product over the sum to the power sum over two resistors, right? Two resistors, R1 and R2. So this is how I can calculate the maximum power from this simple circuit. And depending on the nature of the circuit, that means you have to always get VTH and RTH, and this will allow you to get the maximum power. If this is your first time watching this channel, make sure you subscribe and then share the videos with your friends and your colleagues so that they can also benefit from these amazing videos. And if you want to see more of these videos, then make sure you subscribe. See you in the next video. Bye.